This video is a continuation of our look at the fundamental theorem of calculus. We proved, under certain assumptions, we proved part one of the theorem previously. Now we're going to look at part two, and part two is what really allows us to get a firm grip on this area problem. So what we're going to do is, so let's remind ourselves what our goal is, right? So what is our goal? So if we have a function let's say y equals f of x and an interval where x is between and including a and b, we want to be able to find this area. And we want to be able to find the net area exactly. So what is the exact net area, right? Now, what we proved with the first version of the fundamental theorem, part one, is basically this, that if we define an area function to be the integral from a to x of f of t dt, then its derivative is the original function, f of x, right? So we have this fact and we will make use of it, right? So what I'm going to do is, so for this, our little f of x, so let big F of x be any antiderivative of little f of x, right? That is, and again, we know how to find antiderivatives, so what I'm saying is, so that is f prime of x is equal to little f of x. All right. Well, look at what the first version of the fundamental theorem says, that the derivative of my area function is f of x. But then any antiderivative of, if big f of x is any antiderivative of little f of x, then big f prime must be equal to little f. So what this is saying is, so like you basically combine these two equations. So this tells me that a prime of x has to be equal to f prime of x. This means that the difference between the two derivatives must be equal to 0. Well, if their derivatives, if the difference between their derivatives is equal to 0, then it means that the difference between the two original functions must be a constant. So like if you integrated this, so you would get a of x. If you integrated this, you would get f of x. If you integrate 0, you would end up with 0 plus c, so you'd have a constant right here, right? So what this tells us is that these two functions, they differ only by a constant, right? And essentially, graphically, what this tells me is that this antiderivative of little f and this area function, they're like vertical translations of each other, right? In other words, if you take one function, if you were to plot both functions, the difference between their respective y values would always be the same. It would always be this constant, right? So I can write it like this. So therefore, if I solve this equation, kind of move stuff around, I can get that big f of x is a of x plus some other constant. I just kind of relabeled it. Right? Now, so I'm going to write down an expression. Remember what let me scroll back up. Remember what we're trying to find. We are trying to find the area under our little f of x from or between the graph of f of x and the x-axis from x equals a to x equals b. So I'm going to write down an expression that seems a little strange, but here it is. Oh, why is that doing that? So consider this difference, f of b minus f of a, right? Well, let's see how we can write this down. Well, if I plug b here for x, then I'd have to plug it here for x as well. So f of b is the same as a of b plus c1 minus, and then f of a would be something similar. It would be big A of little a plus c1. Now with that difference, because I'm subtracting, the constant goes away, right? So I would end up with a of b minus big A of little a. But remember what A represents. A represents our area function. So the area function, this part is the integral from A to B under my function, my f of t. So like this. And then minus, and then this term would be the integral from a to a, right, of f of t dt. But again, this is a property, and we've used this property several times now. This definite integral has to be equal to 0. So look at what we have. So what we have left is the integral from a to b of little f of t dt, and then this is 0, so minus 0. So let's rewrite it now. I think we have it, because notice what this is saying. This is the area that we're trying to find, right? That net area. And what I'm going to do, well, in fact, let me go ahead and state it like this, right? But look at that. That's equal to f of b minus f of a. So finally, we have a specific formula for our net area, right? And this is what the theorem says. Let me state it, and then we'll do some examples, right? So this is our theorem. So essentially, I gave you the proof before stating it. Now this is our FTC, and this is our part 2. Now if you look at other resources out there, other textbooks and so forth, they sometimes prove this one first, and then they derive our part 1 after. So sometimes the sequence is flipped, but logically you could go either way, and that's why they're equivalent, right? So this one says if f of x is continuous and big F prime of x is equal to little f of x. So that means, again, big F is an antiderivative of little f. If that's the case, then we have this conclusion. And notice what I did in the theorem now when I'm stating it, I stated it using the standard variable x. because it doesn't matter here now if I have an independent variable of t or x or some other letter. The important fact here is that this is our net area that we're trying to find, and it tells us how to find it using the antiderivative. So the conclusion of the part 2 is that the integral from a to b of f of x dx is equal to big F evaluated at b minus big F evaluated at a. So you take the antiderivative of your function, your integrand, evaluate it at the upper limit, evaluate it at the lower limit, and then take a difference. And there is a shorthand notation that's given for this expression, and this is what it is. It's the big F of x, and then you have a vertical line, and what we do is we put the lower limit at the bottom there, a, and then the upper limit there. So this is sometimes used as a way to abbreviate this expression, right? And this is our very powerful, very useful fundamental theorem, and it is something that we're going to use. I mean, I can't tell you how many times. You should keep a tally of how many times you actually use this theorem in this course, and I'm sure you'll probably hit over 100 times. Right? So let's look at a couple examples of this. And what I'm going to do is just focus on the evaluation, focus on the notation, so you get used to it. Right? So let's start with number 1. So what I'm going to do is write down different definite integrals, and just evaluate them. Right? Not overly complicated, but just so that you can get a sense of what's being done. So let's say you have to evaluate the integral from 0 to 1. And let's say your function is x squared minus 4x plus 5 dx. Right? So what we're going to do is look at how we typically express or answer, and then evaluate. So the first thing we want to do is to find the antiderivative of x squared minus 4x plus 5. So I'm going to write down the antiderivative, and I'm even going to include the plus c, and then we're going to see what's going to happen to the plus c. In fact, it's the same thing that just happened in the proof, if you remember what happened. So let's write down the antiderivative. So I'm going to do this part now. So it's 1/3 x cubed minus 2x squared plus 5x, and then we use this vertical line to show now that we're going to do 2 function evaluations. So we're going to evaluate our antiderivative first. Oh, I forgot my plus c. Let me put the plus c in. So we got a plus c, and then like this, and then 0, first at 0, and at 1, and then we're going to take the difference, right? So that's this part, just kind of the notation. Now let's do the actual process. So plug the upper limit in. So I'm going to do this part now. So this is 1/3 times 1 minus 2 times 1 plus 5 times 1 plus c. I'm going to put that in parentheses. Again, that's all of this. And then we have to do the same process, but now substitute the lower limit in. I'm going to put that here. So that will be 0 minus 0 plus 0 plus c. And then the theorem says I have to take a difference. Right? So I have to take a difference. But in taking the difference, what happens is the constant cancels out. So all I'm left with is 1/3 minus 2 plus 5. The c cancels out because I have c minus c. And all of these terms just happen to evaluate to 0. Right? And then what we have here is, so we can write this with fractions with denominator 3. So 6 over 3 minus 15 over 3. I'm sorry, plus 15 over 3. So we end up with 10 thirds. So this would be 10 thirds. And that's the value of this definite integral. Now, what I'm not going to do in these examples right now is focus on the area part of it, because we know this represents an area. I want to focus on the evaluation part, and then once we master this, then we can put it all together. So I'm not even going to talk about area. I'm not going to sketch any regions. I'm just going to do a few more examples illustrating this theorem. Right? Let's take a look at this one. Let's do a trig one. Let's say we have the integral from 0 to pi over 4. And let's say the function is 3 sine of 2x dx. Right? Well, again, what this theorem is saying is that in order to evaluate this, we first find an antiderivative. Right? So the antiderivative of 3 sine of 2x is negative 3 halves cosine of 2x plus c, and then we evaluate it at 0 and at pi over 4. So let's put this in parentheses so we get the correct order of operations. So negative 3 halves. This would be the cosine of, and I have to double this, so it becomes pi over 2. So cosine of pi over 2, and then plus c, and then minus, that's what the theorem tells me, plug in the lower limit. So negative 3 halves cosine of 2 times 0 is 0, so that's going to be 0, and then plus c. So let's see how this simplifies. The cosine of pi over 2 is 0. So all of this is 0. So I have 0 plus c. And then here the cosine of 0 is 1. So I have minus negative 3 halves times 1. And then that will give me a positive 3 halves. So positive, and then 3 halves, and then, oh, wait a second, and then distributing it, that negative to the plus c makes it a minus c. So we end up with 3 halves for that answer. All right. Now notice in these two examples, going from this step to this step, when we included the plus c, because there's a minus in our fundamental theorem, that constant goes away. So the plus c really wasn't important. The same thing down here. You know, once we simplify, the constant goes away. The plus c and then your minus c there, it all cancels out. So in general, when we're evaluating a definite integral, we only need like the functional part, like the base part of the antiderivative. We don't need the plus c. It's just an extra thing that's going to end up being canceled out anyway. So let's make a note of that, right? All right, so when evaluating a definite integral and finding the antiderivative, right, what can we say? I'll just say plus c is not needed. It's not wrong if you put it there, right? Because again, remember what we said, the big f of x is any antiderivative. So you could add any constant there. So you could even choose your constant to be 0, and that way you wouldn't have to write the plus c. But if you put it there, just make sure that you do the algebra correctly so that it does cancel out, because the answer has to be a specific number. So if you start with a definite integral, because that definite integral represents a certain net area, then it has to be a constant. So you can't have like letters in there. All right. Okay. So let's see what it looks like if we utilize this uh, little property that we don't need it. Let's do another type of function. So let's say it's a exponential function like e to the 2x dx. And here we're integrating from 0 to the natural log of 3. Right? Well, antiderivative of e to the 2x is 1/2 e to the 2x. And then that's now evaluated at 0 and the natural log of 3. So you notice here I didn't write the plus c, right? Because I know, thinking ahead, that plus c is going to cancel out because of the minus sign. So it gives me just a little less to write, so I can be a little bit more efficient in my work and also less prone to errors. Because what if you made an error and didn't cancel out the constant? Then your answer would be incorrect, right? Because the answer to a definite integral must be a specific number, right? Okay, so we could do now other things you can do to help you simplify and minimize errors, like when you have a constant multiple here, so a constant multiplying a function. You could take the constant, like you can almost factor it out since there's going to be a difference, and then plug in the upper limit, so you'll have e to the 2 times the natural log of 3, and then minus, again because of our theorem, e to the 2 times 0. Right? So if you wanted to, you could have the 1/2 in front of each of these exponentials, or you could factor it out and multiply at the very end. Now let's look at these e's. I think, hopefully you see that this simplifies to 1, so that's really nice. And we know that there is a relationship between e and ln, the fact that they're inverse functions. So in fact, let me remind you of a couple properties for e and ln. If you have the ln of e to the x, then that is always going to be x. And this is for all real numbers. If you switch it around and do e to the ln of x, that still simplifies, but this property is only valid for x greater than 0, right? In other words, it has to do with the domain of which function you evaluate first. The e to the x is evaluated first here, and the domain of e to the x is all reals. The ln of x is evaluated first here, and its domain is x greater than 0, right? Its natural domain, right? But in order to use this property, I have to somehow do something with this 2. And there's one more property that I'm going to write down, and this is a nice property of the natural log function. And if you have a constant times the log of something, right, as long as, again, everything is well defined, this is the same as the log of that thing raised to the power p. So what it allows us to do is to take up not just constants, but expressions that are, or an expression that is multiplying the logarithm, make it a power of what's inside the logarithm. So this e to the 2 times the natural log of 3 can be simplified as e to the ln of 3 squared. So I bring up that 2, I make it an exponent there, and then I'll close my parentheses. So now let's see what this simplifies to. So we got 1/2. This is e to the ln of 9, and we still have our 1 there. And now we get to use this property, right? We get to use that property. So we have 1/2. The quantity e to the ln of 9 is 9 minus 1. 9 minus 1 is 8. 8 times 1/2, that is equal to 4. All right? So again, it's a really useful property, this fundamental theorem. And once you get used to the idea that evaluating a definite integral means essentially two big steps. Finding the antiderivative, right? And any antiderivative will do, so we don't need the plus c. And then evaluate that antiderivative and take a difference. So this step right here, that's the true calculus step, and that's what we proved earlier with the fundamental theorem. And the rest of it is just algebra. All of this is just algebra, right? So let's do one more example illustrating this. Again, I'm just trying to use different functions. Notice every definite integral had a different function, just to kind of give you the flavor of it. So let's say our last one is 0 to 1, and it is 1 over 1 plus x squared dx, right? Now this function, you see the 1 over and you might be inclined to think that it's a natural log, but it's not a natural log because the denominator is not linear, right? What we have is a quadratic in the denominator, and what you should remember is that this is your arctangent derivative from Calc 1. So the antiderivative of 1 over 1 plus x squared, that's arctangent of x, so you can write it like that. I've explained previously why I am not a big fan of this notation. I do prefer something like this, because too often you see this -1 and you think, oh, -1 power means a reciprocal. It's not a reciprocal, not for this particular type of inverse trig function, right? So if we're using this, so then this is arctangent of 1 minus arctangent of 0. The other thing to keep in mind is when you're using trig and inverse, trig functions, if you are going to, let's say, use a calculator, be sure to have it in radian mode, right? And in radians, the arctangent of 1, it's that special angle. It's pi over 4. And then the arctangent of 0 is 0. So this definite integral works out to be pi over 4. Right? Again, I just want to point out that here is the big calculus step, right? And then the rest is just evaluation, whether it's a algebraic function, exponential, logarithmic, or trigonometric. It's just evaluation from this point. The big skill here is making sure that we're able to find our antiderivative and then evaluate it correctly. All right. So mark this one as a big one, and it's a huge step. I will be using this result so many times. Like I said, you should keep a tally and how many times you use this theorem from here on out. So hopefully you found this helpful and informative, and I'll see you in the next video.